Hello, everyone. Today, we will talk a little bit about practical issues and continuous wave transceiver structures. We've learned about several modulation techniques and their demodulations. Note that in practice, these communication systems operate in the RF spectrum, which is regulated by governmental bodies. And let's see, there are various services and communication systems that are allocated portions of the spectrum. For example, if you look at a screenshot from your RTL SDR spectrum sweep, sweeping frequencies from around 100 megahertz to 1.8 gigahertz. Okay, we see that there is at the lowest edge of the spectrum, there is frequency modulation radio, FM radio. After that, there are satellites, some mobile, handheld systems. Okay. Digital audio broadcast and DVB-T. Here, there's a band that all of us use a lot during our daily lives, which is LTEA, fourth generation cellular communication system, around the 900 to early gigahertz range. The GSM, the second generation GSM system still exists around the 900 megahertz band, and UMTS, the data service for GSM, is close by. And more satellite communication is in the gigahertz range. So also, indoors, we use a lot of ISM-based systems, and increasingly some IoT services using transceivers such as LoRaWAN. They exist in the small gigahertz ranges. 5G, when it gets operational, it will be in the higher gigahertz ranges. So basically, the spectrum is pretty crowded. At the moment, we're seeing only a portion of signals here. The spectrum is actually quite crowded. And when you're interested in receiving your own signal in a particular band, what do? In the presence of this myriad of transmissions, some weak, some strong, how do you tune to the desired band and reject undesired signals? Okay, so now the easiest thing that comes to mind is you just go ahead and demodulate at the carrier frequency. Okay, what would you do in a simple-minded approach? First, you would have a tunable bandpass amplifier. Are you operating at 900 megahertz? You would tune it to 900 megahertz and then feed the output of this amplifier to a demodulator and then give it to the sink of the application, whatever it is. Is it a phone? Is it a TV? Now, there are various problems with this direct approach, and we will discuss these. Another idea is down conversion directly to baseband. And this is sort of like a more modern approach. You use an RF amplifier to get the signal down to a local oscillator frequency. Using a local oscillator frequency, down to baseband. Now, there are problems with this as well, because the local oscillator frequency has to be equal to the RF frequency, and that requires an amplifier front end that operates at rather at a rather high center frequency. Okay. If you do this, the result, of course, is in baseband, so you can low pass filter it and then process it further, feeding into the demodulator. Okay. Now, for both approaches, you would need a tunable RF amplifier, and it is a challenge to build this amplifier. It has to be tunable, as well as having good quality that is and working in a large range of frequencies. Those are quite tough design criteria to satisfy. All right. Now, in order to mitigate the handicaps of these, this direct approach, we will study something called the heterodyne receiver. Okay. That said, although the heterodyne receiver is the classical and tried and true approach, recently, in the last decade or so, homodyne receivers, meaning converting directly to baseband through, through using this local oscillator frequency at the RF frequency, are gaining importance because of our digital radios and digital receivers. However, we will focus during this chapter essentially on heterodyne receiver design. Heterodyne receiver means there's essentially an intermediate frequency at which the receiver works. So no matter what RF frequency you're trying to receive, suppose this is the RF signal that you're trying to receive, you tune the local oscillator such that the resulting signal after the mixer is going to appear at a desired intermediate frequency that the receiver is set to operate at. So how do you do that? You could either down convert or up convert. To down convert, you use a local oscillator that is larger than the RF signal, and then the difference is going to be so the difference here is FIF, or so basically when receiving the RF, you down convert to FIF, and then when you are transmitting, right, you use the local oscillator to take the signal at IF and up convert to the desired RF frequency. Okay, so here is an example circuit operating at IF. So the LO comes in here and the RF input comes in here. So this is a modern mixer circuit. And the IF output is provided. Okay. Now, the main problem with local oscillators is local oscillator leakage. This local oscillator frequency leaks onto the IF output. If that happens, it's going to cause certain problems later on in the demodulation stages, because it can self-mix and cause unwanted DC components as well. Okay. So, but the basic idea of a heterodyne receiver is we want to operate at a certain intermediate frequency FIF, and that's why we tune our local oscillator in order to bring whatever the down convert, whatever the radio frequency is, to FIF. And we do this at the receiver. So this is the RX part. At the transmitter, we process our signal at IF. We produce our modulated signal at IF first, and then we up convert to radio frequency, which we then transmit into the air. Now, let's talk about the superheterodyne receiver structure. It's a classical, quite ancient receiver structure. So the idea is what we just discussed. Take the RF amplifier, tuned appropriately, such that after the mixer with the local oscillator, the frequency of the received signal is going to be at IF. Okay, and then this is passed into the demodulator. So the local oscillator should be at FC plus or minus FIF. Okay. You can use a local oscillator to select a channel. If this is a radio receiver, you select the radio channel this way. Now, there's going to be some problems which you can infer from this FC plus or minus FLO mixing part. What is that problem? The problem of images forming on top of our signal. So suppose this is our intended signal. This this orange signal, suppose, is our intended signal. Okay, spectrum shown in orange. Okay, it is centered at FC. Right. Now, our RF amplifier, since it's a high center frequency, it is not expected to be very sharp. This is operating at 100 megahertz, for example. Okay, so its characteristic is not expected to be that sharp. Think about our signals. Our signal is narrowband compared to it. All right, so it's going to admit some portion of the spectrum
Hocam şu an sesiniz gelmiyor. Mutlu gözüküyorsunuz.
Thank you. My connection was lost. Let's see if everybody's here. Right. I should actually pin my video. One moment. I was trying to pin this video. Okay. Now we can continue. So let's see if I'm recording. Yes. So in addition to the intended signal, which is at FC, okay, the RF filter is going to admit a whole range of signals around it. Okay. Now, let's in particular focus on the signals that are admitted around Fc minus 2 FIF. Notice that the distance of Fc minus 2 FIF to the frequency FIF is equal to Fc minus IF. So if you use the local oscillator frequency Fc minus FIF to bring Fc down to FIF, then you will also be bringing Fc minus 2 FIF to FIF as well. So what will happen after the mixing? After mixing, these signals will come on top of these signals. Although they've been attenuated a little bit by the RF filter, they will still be there. So what we will be seeing at the intermediate frequency is some interference that is called an image. Okay, you can see the green triangle on top of the orange desired signal. Now, this, once it gets on top of our desired signal, then there's nothing we could do. It is going to act as distortion. So the remedy is to try to lessen this effect before it happens. That's the intended remedy. Now, one thing is you could try to use a higher quality RF stage, but the challenge is you want it to have a high bandwidth because it's at a high center frequency in order for the RF amplifier to be kind of flexible, affordable, etc. The IF stage is a narrower filter at a lower center frequency. So the IF filter also can afford to be low Q, low quality. Okay. So if we can sort of, if we perhaps use multiple IF stages, we will take, gradually bring the RF signal to IF. We will take care of this image problem. Okay, so one obvious expensive remedy is to use a very good, very sharp, high quality RF filter. The other remedy, it is used traditionally, is to use either a large IF frequency so that the image is going to be far away from the desired signal, and that will be within the attenuating region of the RF filter, or use more stages. This is the most common approach. So here's an example of using more stages. After the RF amplifier and filter, there's a first local oscillator bringing the signal to the first IF frequency. After the first IF amplifier and filter, we put another local oscillator, another mixer, and bring it down to the second IF frequency. Okay. Another problem, in addition to the image problem, is spurious responses that are created due to harmonics that appear due to the nonlinearities in the RF amplifier. So suppose the local oscillator signal contains harmonics or spurs. It's quite difficult to avoid this. Now, if the RF amplifier is operating in a nonlinear region, the harmonics are going to be mixed. Think about it, when we square a signal, for example, we observe double frequency components, or when the third power of a signal is present, triple frequency components are going to be present, as you know from our previous analysis. Right. So if LO, FLO, 3FLO, etc. are present, notice what happens after the mixing and the IF filtering is that any multiple of FLO that satisfies this difference to be FIF is going to get admitted into the detector. What is this difference? The difference from a multiple of the center frequency, carrier frequency, of another multiple of the local oscillator frequency. Okay, so basically, here's the bottom line. If our local oscillator is producing harmonics due to the amplifier nonlinearities, okay, then we will be admitting not only FC, but multiples of FC from the air. Because when these frequencies are mixed with a multiple of our local oscillator frequency, they're going to result in FIF. And these are called spurs or spurious responses. Let's do an example to make this concrete. Suppose we have an IF frequency equal to 455 kilohertz. The desired signal is at 1 megahertz, and the local oscillator frequency is set to 1.455 megahertz. All right. Now, let's take a look at a bunch of frequencies from the air that we could potentially pick up. Now, the desired signal is here at 1,000 kilohertz. Okay, so basically 1,000 minus 1,455. Okay, let me write it here. Is going to give us the FIF desired. Okay, so that is not a problem. That is admitted. However, look at the following. Now, look at the following. 500, for example. 500. Okay. Now, this 500, when there's a second harmonic, okay, it's going to appear as, twice 500 is going to be 1,000. So it is going to appear also as a spurious response. Okay, so we will be picking up the signal at 500 kilohertz. How about, think about this one, 1,910 kilohertz. Okay, that signal, the signal at 1,910 kilohertz is directly picked up, even if there is no nonlinearity, as an image, because 1,910 minus 1,455 is going to give 455. So that's going to be trouble for us. That's the image. So we have a desired signal, the image, and a bunch of spurious responses. What are the spurious responses? 500, 955, 1.2 megahertz, 1.68 megahertz, 2.4, 3.3. Now, in order to reduce the effect of these things, of course, the better the RF amplifier, the better, the more quality the RF amplifier, the more reduced they will be. These interference components will be. Okay. Of course, the harmonics are hopefully weaker to start with as well. Okay. Now, your RTL SDR, as you know, is a modern superhet receiver with analog and digital parts. It is operating at IF frequency equal to 0. Okay. The analog front end has a low noise RF amplifier with an image rejection filter. So it is built in 2 stages, RF amplifier plus filter. Now the FLO is controlled by a PLL, fractional phase lock loop. A fractional phase lock loop. In order to bring the signal directly to baseband. So IF is baseband in this case, meaning FLO is tuned to the FRF. Okay. And then there's an active gain control, which we will be defining in a few slides later. After this, the signal is filtered and converted to a digital signal. It is processed in phase and quadrature components digitally. And the output is given to the USB port. So this is a modern Heterodyne 0 IF receiver. So heterodyne is when there are different frequencies that exist in the transmitter. Heterodyne stands for, well, only one frequency, and that is the RF frequency, and the other is baseband. Okay, so this is an integrated circuit that does this. It takes signals from 70 megahertz to 6 gigahertz, and the instantaneous bandwidth can be up to 56 megahertz. So a pretty successful IC. The LO frequency tune step size is 2.4 hertz. It is incredibly precise. This IC is used frequently as a building block of software-defined radios, and this is the industry trend nowadays. Now, what is the automatic gain control that we saw here? Active gain control or automatic gain control. Now, of course, when the RF signal comes to you from the air, it's not at a constant amplitude. It keeps oscillating due to various problems in the propagation environment, various issues, physical phenomena in the propagation environment. But we usually like to keep the gain constant for the later stages of a receiver for proper operation of the filters and other components. So automatic gain control is a method to keep the gain constant through feedback. So after the filtering and amplification in whatever order they are, there is a mixer with the local oscillator, and the result is fed to a stage of variable gain amplifiers and filters with a feedback loop. So now the detector signal is fed to the automatic gain control filter, which tunes the IF variable gain amplifier. Okay, so when the received signal has low gain, we tune this amplifier to increase the gain. If it has high gain, we tune the amplifier to lower the gain, etc. So that the signal going to demodulation is going to be more or less at constant gain. So that's one of the important circuit components. There's also an automatic frequency control to take care of frequency offsets. Okay, so in this case, the filtering is done to control the local oscillator. This is just like a phase lock loop. So suppose after the FM suppose this is an FM demodulation system, the output of the FM demodulator has a certain offset frequency, suppose. This is going to be fed into the low pass filter, and that is going to cause the local oscillator to fix itself in order to ensure that the instantaneous frequency is corrected to derive the frequency offset to 0. So all of these things are done using feedback loops. Now, how do we send multiple signals over the same communication medium? Whether it is RF or whether it is a wired transmission. Now, one of the classical ways of multiplexing signals together is frequency division.
Hocam sesiniz
Yes, please.
kesilip duruyor aralarda. Ben duyamıyorum.
Well, is it due to the connection? I will try to speak closer to the receiver. Is it better now?
Ya bizde bir sıkıntı yoktu ama belki İbrahim'in kendisinden kaynaklanıyor olabilir.
So frequency division multiplexing. One classical example is called the public switched telephony network, also called the plain old telephone service. The basically wired telephony, right? How do we carry multiple calls over a single wire? Okay. Now the idea is transmit each call over a slightly different frequency band and then add them together. Okay, so there are individual subscriber devices here. They are, given slightly different frequencies. They're all multiplexed together here, and then they come to the switch. And then at the switch, various terminals like this get combined. And this is a hierarchical structure. So if you go to the system diagram for this FDM structure, there's a problem hearing me?
Bende sorun yok hocam da herhalde bir arkadaşınız.
So here we see a system diagram for a frequency division multiplexing system. message signals are each low-pass filtered and modulated, but modulated at different frequencies, such that the bandwidths of the modulated signals do not overlap. They're all added together and given to the channel. After transmission, how do we receive them? You would use bandpass filtering at the desired frequencies, followed by demodulation and low-pass filtering. Pretty simple. So if we look at the public switch telephony network, the signals generated at homes are classically between 300 hertz to 3.4 kilohertz voice signals. They are filtered to be in this, live in this band, but then they are placed anywhere between 10 to 20 kilohertz. Okay, so you can fit a number of different home signals in a given terminal, and then you transmit the collection to the central office. Okay, obviously you need to put guard bands in between the signals. So when we go from neighborhood to town, town to city, there's going to be a hierarchical structure where different bands are collected and added together. Pretty simple idea. But the idea resonated into the modern cellular communication systems. Right? So to go a little bit into the details of these frequencies, FC1 could be 108 kilohertz, FC2 104 kilohertz. You see that there's 4 kilohertz difference in between. Although the signal itself is living in a 3.4 kilohertz band, together with the guard bands, we leave room for 4 kilohertz. Okay, so these individual channels are mixed together, and then they form a group of 60 to 108 kilohertz, and then groups are multiplexed together, etc. So this is the FDM standard by the International Telecommunications Union. 48 kilohertz is formed by 12 voice channels, so 4 kilohertz per voice channel, and this forms a group. And then 5 groups are frequency division multiplexed together to form a supergroup containing 60 voice channels. And then 10 supergroups forming 2.5 megahertz are called a master group, and then the jumbo group, etc. So this is a standard. So if you obey the standard and if you build a telephone receiver, your telephone is going to be able to get plugged into this system. Standards are important because all constituents, meaning equipment manufacturers, component manufacturers, users, they know what to expect from a system and what they need to do, and they get assurance that once they produce their product, they can sell it, right? And companies reduce their costs by obeying to a standard, because the more standards you have to comply to, the more R&D, the more different products you would need to develop. Okay, so standards are important in telecommunications, and telecommunications is quite famous for very, very, very, very detailed and long standards, including 3GPP, for example, the current cellular communication standardization body, the 802.11, the Wi-Fi standardization body, and many, many other things. IETF for internet standardization, for example. Now, we talked about FM, And you may be wondering, well, in my car radio, there is stereo FM reception. How does that work? And that is an example, canonical example for how when a new concept comes in, it is designed to accommodate the earlier standard and keep it in place so that while the new technology works, the older technology is undisturbed. It continues to work. Okay, so here's the idea. Stereo FM transmission is so basically when stereo FM is transmitted, and if you had a mono FM receiver, you would be able to receive a monotone FM signal without a problem. Right, that is the sort of the downward compliance example here. Backward compliance. Okay, so how is stereo FM done? The left and the right audio signals are recorded separately in the studio. So you have two signals. The signal, the sound signal coming from the left-hand side of the room, and or if you want concert hall, the right audio signal coming from the right-hand side of the studio or concert hall, and you want to transmit these in a way that they will be heard by the user from the left-hand side speaker and the right-hand side speaker. How do you combine them? This is a creative use of FM with double sideband suppressed carrier modulation through frequency division multiplexing. Isn't it nice that now you are able to understand all of these terminologies, right? So this is the left audio signal, ML of T, and this is the right audio signal, MR of T. Okay, here's the idea. On this, the first channel, on the top channel, here, transmit left plus right, that is ML plus ML plus MR. On the bottom channel, transmit ML minus MR. Now, when you transmit ML plus MR, put them through combine them with a 19 kilohertz carrier. Okay, take L plus R, combine them with the 19 kilohertz carrier, and then send the result to an FM modulator. Take L minus R, mix it with a 38 kilohertz signal. Okay. Also add it to the left plus R plus the carrier and put the whole thing to the FM modulator. So let's take a look at this at frequency band, what's going on in frequency domain. Left plus R is here at baseband. And this is my carrier at 19 kilohertz. And this is my left minus R, modulated to 38 kilohertz through double sideband suppressed carrier. So none of these things are overlapping, as you can see. What do you think is the reason for the carrier for 19 kilohertz?
İndeks olarak kullanmak için hocam ileride 38'i çekilecek ileride alıp.
Right, exactly. We're going to use, that is going to aid in the demodulation, right? Now, so left plus R plus 19 kilohertz carrier plus left minus R modulated to 38 kilohertz. They're all fed into an FM modulator. So what happens at the receiver? First, demodulate the whole thing using FM demodulation. And then we will worry about demultiplexing. Okay, so this received signal combined of all of these things comes to the FM demodulator. Now, first, to receive L plus R, we can simply use a low pass filter at 15 kilohertz. Okay. That's recovered. Now, put a 19 kilohertz band pass filter to receive the carrier. Okay, use a frequency doubler. Okay, and that is going to help us demodulate the double sideband signal, which we also further low pass filter to receive the L minus R at baseband. And now to recover the right and left, we will add and subtract these two signals. L plus R plus L minus R is going to give us L plus R plus L minus R minus L plus R is going to give us right, and these could be fed to the individual speakers by the stereo FM receiver. But if you had a mono FM receiver that didn't care about these things, that doesn't have these features, it would only be using this part right here. And it would not feel any difference. Okay, so legacy receivers, legacy mono FM receivers should operate as usual. That is the business requirement in the standardization to be downward compatible. So the technological solution found to satisfy this requirement was to multiply the L plus R and L minus R signals separately. So this is a creative solution example from telecommunications history. Right. Now, FM demodulation, as we said, there is something called gain control in order to keep a constant gain, etc. But that also may not be sufficient. As you know from the theory of frequency modulation, that ideally we have a constant amplitude signal, constant amplitude sinusoid, whose instantaneous frequencies modulated, right? However, in practice, due to the movement of the transmitter, receiver, objects around them, etc., that you will study more in EE 436, there is going to be amplitude variation on top of the signal. That is unintended amplitude modulation. So how do we take care of that? So the unintended amplitude modulation can be represented by a time varying amplitude on top of, multiplying the FM waveform. If you pass it through a differentiator, so how do we demodulate FM? The mathematical approach, the simple-minded approach, is put it through a discriminator or differentiator, right? Of course, in practice, there's a phase lock loop, etc. But the direct path is the differentiation. So if you were to differentiate this, you would not only differentiate the FM, but you would be differentiating this time varying amplitude. Differentiation of a product of two things. Derivative of the first one times the second plus, you know, you also get the first one times the derivative of the second. So because of the derivative of the second term, right, we will be getting wait. So this is what we would normally be feeding into the envelope detector, but there is this time varying signal multiplying it here, and that is amplitude modulation. So this A of t is going to create a problem if we don't take care of it. Okay. So somehow, if A of t was arranged such that its derivative was 0, we wouldn't have any distortion. So how do we get rid of the amplitude variation? We use a limiter. So all the FM demodulators actually are limiter discriminators. Okay, first there's a limiter, and then a bandpass filter, and then the differentiator, even if there's a phase lock loop. Okay, so rewrite the received signal as A of t cosine theta of t, where theta of t is the time varying phase, and any negative amplitude is absorbed by the phase. And then now pass it through the limiter. It's like a signum function. Notice that AM is going to disappear because of the action of the signum function. Okay, and to check this mathematically, when you put cosine into a signum function, you will notice that the cosine can be represented as a Fourier series. And I mean, this, I'm sorry, not the cosine, but the signum of cosine can be represented as a Fourier series like this. And after bandpass filtering, we will essentially have this term, which is an almost clean FM signal that varies slowly with time and almost has 0 derivative. This extra phase component is slow. So essentially we have an almost clean FM signals. So FM receivers are usually in the limiter discriminator form. I recommend that you go through this short mathematical derivation as homework. So another classical application of the phase lock loop is the Costas loop. This is an alternative to all the squaring loop that we saw for double sideband suppressed carrier demodulation. We saw the PLL for FM demodulation, but this PLL application, which is known as the Costas loop, works for double sideband suppressed carrier demodulation, just like the squaring loop does. So the double sideband suppressed carrier comes into the demodulator. What do we do? Well, there is a low pass filter here that produces Y1 of t, which is filtered and fed into the VCO. Okay, and that forms the carrier. So this is the carrier extraction. This is the carrier extraction loop here. Okay, and there is another loop here. Okay, so this is a sine. Okay, sine multiplying the sine and low pass filtering. Okay, that is going to give us y2 of t when mixed with y1 of t is going to feed the input of the loop filter. Okay. Now, if you check the steady state behavior of this Costas loop, this signal C of t is twice cosine W0t plus some initial phase theta 0. Okay. So theta 0 well, this can also be expressed in terms of the carrier frequency WC as WC plus theta R. So there's a time varying phase here that is formed of a linear phase plus a constant theta 0. Here is the analysis in more detail. Now, Y1 is a low-pass filtered version of the incoming signal times the VCO output. Okay, and that is going to be sine theta S minus theta R. Now, ideally, this difference theta S minus theta R is small when the loop is in lock. Okay, so Y1 then is going to be proportional to M of t times some difference theta S minus theta R. Okay, how about Y2 of t? Y2 of t, the output of the demodulator. Take Y1. Take S and multiply it by the sine generated by the 90 degree minus 90 degree phase shifter from the VCO output. And we form this M of t cosine theta S minus theta R. Okay. Now, when theta S and theta R are close to each other, Y2 of t is close to M of t. Now, the idea is we are multiplying Y2, mixing Y2 and Y1, and this is the result. Okay. 1/2 m squared of t times sine of the difference of the two angles. This provides a term for feedback. The loop filter takes this and if this thing is negative, it increases the VCO frequency, and if it's positive, it decreases the VCO frequency. And this will continue until theta S and theta R are close together. So this is a sort of a complicated looking design. It's known as the Costas loop. It's like a PLL, and it's used to demodulate double sideband suppressed carrier. Earlier in our demodulator structures that we studied for double sideband suppressed carrier, we mentioned the squaring loop, which is a little bit simpler, easier to understand than this Costas loop. And we also, of course, said, you know, whenever you have the carrier available somehow in the receiver, you can easily demodulate double sideband suppressed carrier. Any questions?